what do I mean by data fundamentals? And there's a very famous quote by Donald Rumsfeld, who's a former Secretary of Defense in the United States. And when he made this quote, or when he said this, he was roundly ridiculed for having said it. And I'm not a big fan of Donald Rumsfeld in general. Like, he's not my kind of person. But I feel that there was something very, very meaningful about what he said there. And you might have come across this quote in your everyday activities or professional activities. I'll read it here just so that it's worth keeping in the back of our mind. Reports that say that something hasn't happened are always interesting to me because, as we know, there are known knowns. There are things we know that we know. There are known unknowns, that is to say, there are things that we now know we don't know. But there are also unknown unknowns. There are things we do not know we don't know. And I guess you can take the position that anything that we do with data is to try to get at the unknown unknowns, to try to discover things that we didn't know about the data. Like the things that you know, it's not that they're not interesting, but you know them, and you know that you know them. The known unknowns, things that you know that you don't know, that's perhaps you can work with that as well. You're trying to figure out the specific value or the specific insights that you don't know that you know must be there, and that could be something to do with data as well. But to me, at least, it is the unknown unknowns that are the most interesting, especially when it comes to anomaly detection. We don't mention about the unknown knowns because obviously that one doesn't make sense. But if you keep that in the back of your mind, that we are forever riddled with the unknowns, and that this is really, we can't get rid of those. The best that you can hope to do is to reduce or shrink their size so that the territory that is unknown gets smaller every day or every year, then that's a positive thing. But in reality, we will never get to the point where there are not unknown unknowns. Okay. So when we say that with data we're seeking the truth, it's true, we're seeking the truth, but we can never get the full truth. There's always going to be unknown unknowns. So here's what we're going to talk about. Give you basic data concepts, again, just to make sure we're all on the same page. And some practical definitions as well. I'll talk a little bit about workflows and pipelines with the advent of big data. Just to say, data that we're collecting large volumes and it comes in continuously. We can't just do data analysis the way that you might have learned to do it 20 years ago when you took your university courses, or not as long ago. Some of the faces here don't look like they're old enough to have been at university 20 years ago. We can't do it the way we used to do it anymore. A lot of the data analysis process, a lot of what we do to get the data insights now include setting up the infrastructure and being able to access and query the data that we have efficiently, effectively. Right? If we're working with gigantic data sets and it literally takes 20 hours to make any one computation on your local machines because the data sets are too big, then you will never be able, to extract insights from your data. We'll talk a little bit about models and systems thinking as well. This is something that I bring in from a cognitive science colleague of mine, and she's very big on understanding the system that we're modeling, what the data is meant to approximate. And we'll talk about that. To me, this is quite important. And while at the end, if we have some time, give you a little bit of a breakdown on ethical considerations and best practices. Presumably, as an organization, you already have a bit of a code of ethics as to how you work with data. I know as public servants, you do have a code of ethics. There's slight modifications or slight improvements, if you want, that we need to make when we're dealing with data, at least in my opinion. course, it's easy for me to talk about these things. I'm coming at it from the outside. I am not a public servant. I am not really restricted or bound by the same set of rules that you are. I have more freedom. In particular, I have more freedom to turn down projects that might be harder for you to do as a public servant. But we'll talk about it a little. Let's talk about data. Everybody is familiar with data. What is data? What is that? Right? Often you'll hear people say, oh, data is simple, it's information. But you can have data without information. Right? What Daniel Keyes says here is that you can't have information without data, though. It would seem as though there's this conceptual idea of what data is. Often people will say, it's easy, it's a spreadsheet. Anything that you find in a spreadsheet is data. And that's true. I mean, anything that you find in a spreadsheet is data, but there are things that are data that are not actually found in a spreadsheet. Is this data? Here's another question for you. Is data singular or is it plural? Do we say data is or do we say data are? What do you think? Who votes for data is? Who thinks we should be saying data are? Right, if you go solely on the Latin, the singular form is datum and the plural form is data. I'm not even sure that I'm pronouncing this properly, right? I mean, is it data or is it data? That's another question. This one is less interesting. But there's a pretty big conceptual jump between thinking of data in the singular term and thinking of data in the plural form. It's not unlike how you view the United States. I mean, if you think of the name United States, it's a collection of states. If you think of it, when you speak, if you say the United States is a country, but now you're basically thinking of the union, a collection, as the thing. But if you say the United States are, you're viewing them as, well, a collection of individual states. And I believe right now in the vernacular, people are using the United States in the singular form, even though it's technically speaking a plural term, states with an S. And that betrays, if you want, a shift in the way, well, the Americans saw their country as well. Like once they start thinking of the United States in the singular, then the collection, the congealment has been complete. It is not a collection of individual states. It is the whole of the country. With data, it works the same way. If you think of data as being singular, data is, what you're really doing is you're viewing data as a whole. And if you think that it's meant to be plural, you're viewing each individual entry, each datum, as the most important part of the data set. And I'm here that there isn't an actual clear-cut answer as to which one is best. It really depends on your view of specific data sets and what it is that you're going to be doing with the data. So, is this data? These bits of information. One of the challenges we have as well, it's pretty hard to define what data is. I would agree, to me, this is data. Now, without context, this is sort of useless. Is this data that refers to one unit for which I've taken various measurements? Or is this a collection of 4 completely disparate datums that I've just put together? I don't have any context. I don't have metadata to make sense of what it is that I'm seeing. We might not agree on what data is. We might not have a perfect definition on what data is, but one of the things we do agree on is that data should allow us to talk about objects and their attributes. Here we have an object. It is an apple. Do we all agree that the object is the apple? Except this is not an apple. What is this? It's a representation of an apple. It's a two-dimensional collection of pixels, which is meant to represent a reality. Now, you look at this, I think, Jen, I saw you right away, you were like, yes, this is an apple. And nobody in their right minds would disagree with you. This is meant to be an apple, and we literally don't differentiate between the representation and the actual object. It's so clear what is meant to be represented here. But you will never be able to take this representation in your hands and take a bite out of it. It stands for an apple. It represents the apple. It is not an apple. For many uses you might have in mind, the representation is just as good as the actual true object. But you cannot forget, ever, even for a fraction of a second, that the representation, that bit of information in your cloud, is not the actual object which it is meant to represent. Nevertheless, this object is an apple. Right? We get tired of saying this is the representation of an object which is an apple. We just say the apple is the object. This thing here is the object. Now it has attributes as well. It has a shape, it has color, it has function, it has location, or it has a location, and it has presumably an owner. There might be more attributes, but these are the attributes that I'm choosing to report on. Is this the whole of the apple? We would say, is the signature, is the sum of the parts equal to the whole? Well, in this case, you'd say, no, there's so many more things I could tell you about apples in general, about this apple in particular. And so whenever we record data, we take measurements, we can't ever have the full picture. It is an approximation of the object. So the attributes, the signature vector approximates the object, but keep in mind the object itself is not actually the object here, it's a representation. So whenever we look at data as a window to the world, there's always at least two layers of abstraction. The object is being represented by something which it might not actually be, in this case, and you approximate your understanding of the object as a whole, the unit as a whole, by taking some measurements, hopefully enough measurements so that the fact that you don't have the full picture isn't problematic. So what kind of things are we expecting to see? The shape of this apple is spherical, right? Everybody agrees with this? But it isn't a sphere. You've never seen an apple which is a sphere. And in fact, if you look at different brands of apple, they don't look anything like a sphere anymore. The spherical representation of the shape is not even a good approximation anymore. I think the ones that are very thin at the bottom and end up having like a top heavy, they don't look like a sphere at all. Color red, nobody would disagree that this apple is red, except it's not red. If you look at various points on the representation, you see like some yellowish things. There's even a white glow here. Now, because we have seen apples before in the real world, we recognize what this white glow is meant to be. It's the reflection of a light source. Even though it's not red, it is red. But that requires us to have contextual understanding of the world in which the object lives. Often when you just have data, you don't even know what the equivalent of a white spot here would be, because we don't always understand the context in which the data is found. The function of the apple, well, that's easy. It's food. Well, that's the function for us. If you're the apple tree, the function of an apple is not food. What is it? Why do apple trees grow apples? Yeah, it's a reproduction function. So you see, even though we typically know data when we see it, and here I agree, this is a completely ridiculous example. Nobody in their right minds would waste their time building data that looks like this. And I'm belaboring the point. Oh yes, I'm trying to catch you. You got caught. But the reality of it is that happens with every data set you will ever work with. It's just that we tend to not think about it because we have, over time, over habits, because we've worked with the data set, for a few years, we lose the ability to distinguish the fact that the data is a representation of some real-world situation. And this shift, where we start mistaking the data for the world, that is a very, very, very dangerous place to find yourself in. With this thing, there isn't really a risk, because this is not a true data set, or at least not a very interesting data set. But there is a risk, right? And especially if you've been working with data a long time. We tend to forget about these distinctions. The attributes usually are recorded in some sort of database. And we often call them the fields. If your database is represented, or at least found in a spreadsheet, then the fields will be the columns and the objects will be the instances. That's usually how people do it. There's nothing to stop you from recording things the other way around, where the objects would be the columns and the fields would be the rows. That's feasible as well. It's just that traditionally that's not how we've done it with spreadsheets. And you can describe then an object by just reading the row that corresponds to it. Again, the row is a snapshot, a description of the person. Right? You can use the people in this class as the objects, and we can have a bunch of measurements: our age, our gender, our height, whether we wear glasses or not. You can measure a bunch of things, but you'll never be able to get the full picture just with the measurements. And that's another reality as well. We hope that for the purposes that we have in mind, whatever it is that we measure is sufficient. But we don't always know, and it's not always easy to tell whether what we've gotten was sufficient or not. Does that make sense? I mean, I hope that most of you are looking at this and say, yeah, that's obvious. That's obvious. Yes, I get it. That's obvious. We don't need to talk about this anymore. But, the world of data analysis is actually littered with analyses that are useless because people have forgotten that the data is not the object. The data is a representation of the universe. What do we use data for? Here's an example of a very famous data set. It's called the poisonous mushroom data set. Well, it's the mushrooms data set. Some of them are poisonous, some of them are not poisonous. And in that data set, you have access to the name of the mushroom, a description given by 4 features, 4 attributes, the habitat, the gill size, the odor, and the spores. And then there's a problem, there's a task that you're trying to achieve. Is Amanita muscaria edible, or is it poisonous? If you want to make a link with the anomaly detection setup, the classification problem would be, is this record anomalous or not? Now, I've provided you with a picture here of one of the forms of Amanita muscaria, just so you have an idea, a clear-cut idea of what it is, but the data set doesn't show you the picture. The data set just gives you the habitat, the gill size, the odor, and the spore colors. Do we all know enough about mushrooms to recognize what these things are meant to be? Do you know what the gills of a mushroom are? If you're not familiar, if you take off the cap, some mushrooms, not every mushroom has gills, but if you take off the cap, you'll see little lines radiating from a hub, That's the gills. The odor, well, presumably you pick up the mushroom and you smell it. The spores, do you know what the spores are? I thought for a while that the spores was a color of the little dots here, but it could be that for this specific mushroom that's what it is, but the spores is how mushrooms reproduce. So the little particles that they send out whenever their life cycle tell them to do so. I don't know anything about mushrooms, to be honest. But anyway, they have a color. And for this specific mushroom, they are white. Are we okay with the actual values that are given to these attributes? If I tell you that the habitat of a mushroom is woods, it's like, yeah, everybody, I understand what this is. But here's a few questions to ask about it. Is it that it can only grow where there currently are trees and woods? Or if land was forested before and it's been cut down, is there something in the soil of a former forest that remains foresty enough to be considered a wooded habitat? I live in the forest. I mean, if I look out my windows, I see trees as far as the eye can see. But obviously, where the house has been built is not in the forest proper. Otherwise, a house wouldn't be there. Is this considered the woods still, even though there aren't trees around? How do we define the woods? Right? As it's stated there, you don't know. No idea. You need some sort of meta information about the situation. A gill size, that one should be straightforward. A gill size is narrow as opposed to, say, presumably wide. Sorry. But what is a narrow gill size? I mean, if you even take out a cap and you look at the size of the gills, eventually, presumably when they're closer to the hub, the spacing between the gills would be very small. And as you get further towards the rim, the spacing would be wider. Are we measuring gill size by looking at the angle? Is it clear what's narrow and is it clear what's wide? Without a dictionary that defines these concepts, narrow and wide are completely meaningless terms. The odor as well. How many odors are you able to recognize and name? Are the spores, presumably, it's an easier one to think it's a color. I'm not sure. So, how would we answer a question such as, is the mushroom edible or poisonous? Well, you can use what's called a supervised learning algorithm, which requires you to have a database, a data set of objects with their measurements, together with a conclusion as to whether the mushroom is poisonous or not. So you have a database of the knowledge. Now, if you make the link with the anomaly detection, what this would mean is you have a bunch of records where you know whether there was fraud or not, or where you know whether something was anomalous or it was regular, normal. And what you're going to ask your models to do, and this is things that we'll talk about in the next series of sessions, what you're going to ask the algorithm to do is to try to reverse engineer the connections, the combinations that make something come out poisonous and make something come out edible. Or in the case of anomalies, fraudulent or not fraudulent. Okay? Now, for this to be doable, for you to have a chance to do this, you need to have enough data, and there needs to be an actual link that exists between the measurements and what it is you're trying to predict. We could do an experiment here. I could ask each and every one of you to take out a quarter or a loonie or a toonie and to flip it. We'll flip the toonie, loonie tons of times. So I can ask each of you to do this for like a week, and you just continuously do it. Let's assume you don't need to sleep for like a full week and you're going to be flipping coins and recording, your age and a bunch of information about you, as well as, the temperature outside and just tons of information. And so we reconvene in a week's time once you've done all of this, and we might have, let's say we have 100,000 observations. And we have 100,000 records of whether it was heads or tail when you flip the coin. And we've measured, 18 different things along the way. So you have a big data set. You have a clear-cut task. The task is, I'm going to try to predict whether you flip heads or tails. And it doesn't matter how much data I have. I'm only going to be right about half the time, because there's no connection between what it is that you're trying to predict and the data that you've collected. Right? A coin is like a completely random. You could say, no, some people could learn how to flip it, give it the right spin, and sure, that could happen. But at the level at which we're collecting the data, we don't have access to that type of information. So just because you have a data set, just because you have labels, things you're trying to predict, just because you have an algorithm or algorithms that you can throw at the data set, doesn't mean that you have the ability to make the predictions. That's a huge lesson to learn. I mean, I'm sure you must know that already. Like if you've done any statistical analysis at some point, there might not always be a link. You're not always able to predict what you'd like to predict. Sometimes if you can do just a little bit better than random guessing, like in that coin example, if we were able to come up with an algorithm that was right 52% of the time, as instead of just 50% of the time, this would be a major discovery, right? So the effect that you're trying to predict isn't always going to be great, or you won't always have the ability to do much better than a random guess. But there are instances where even doing a little bit better than a random guess would be a huge boon to your organization and to your, to achieve the task that you're trying to achieve. So we also need to be able to scale back our expectations and recognize when we found some insight which is better than just a random guess. So if you're shooting for the moon, this is great. You want to get a model that would allow you to find, all of the anomalous people, all the people who are, fraudulent or cheating or a front for some money laundering scheme. It'd be great if you could. But perhaps what you can achieve at the end of the day is, I'll find 5% of them that I couldn't find before. And that's also potentially a great achievement. Just because you have data, just because you have a clear task, doesn't mean that the data supports what it is that you're trying to do. Is that disappointing? Do you know that? I mean, have you experienced that? Not necessarily in the anomaly detection context, but have you lived with the reality that data is not necessarily a solution to your problems? Is this something that you've experienced? I do a lot of consulting, other than my academic activities, and I got to tell you, people spend a lot of money collecting data. I don't know what happens at innovation in your specific branch or in your group as a whole, but if you spend hundreds of thousands, millions of dollars collecting data, and it turns out at the end of the day that there is no signal between the data you've connected and what you want to do with it, the temptation to exaggerate effects or to massage the data, to sweep things under the carpet is strong, because it looks bad when you've spent a lot of money collecting data and you cannot get things out of it. But the reality is, you don't get to decide ahead of time whether you'll get something out of the data or not. And you can design your experiments in such a way that you will not right off the bat spend millions of dollars to collect data. You can run a few pilots first to see if you're able to, tease out some sort of relationship that you would like to be able to exploit in a larger data set. But in general, you won't know until you've tried it. If you are working in an organization where everybody is quantitatively minded, everybody's technical minded, people have had this experience that the data doesn't always give you what you want, then you can work with that. You can your supervisors, your superiors will have your back. But if you work in an organization where the higher ups are not quantitative people, they don't necessarily understand that just because you have the data doesn't mean that you can actually do something useful with it, and that's usually a bit of a harder minefield to navigate. Again, I'm speaking as a consultant and a former public servant. I was a public servant for 5 years as well, and I had some experience dealing with these situations. If you go back to this model that I've built here, this decision tree, which is meant to be a model to decide whether a mushroom is poisonous or not, you see that it basically asks you a bunch of questions. It asks a question about the odor first. And if it turns out that the odor of the mushroom was any one of musty, foul, pungent, spicy, fishy, and creosote, then you would conclude right away, without asking any further questions, that the mushroom is poisonous. Because in the data set, presumably, every single mushroom that had a musty, foul, pungent, spicy, fishy, creosote odor was poisonous. Right? Well, we don't know. We don't see the process in which this model was built, but perhaps this is not a ridiculous way to view this. Are you familiar with all these smells? Would you be able to recognize a smell which is pungent? Like I'm not a native English speaker. I don't recognize half of these words. I don't know I can't even imagine what they would smell. Creosote? No idea. Does anybody know what creosote is? Am I even pronouncing this properly? I'm sure I'm not pronouncing it properly. What does that smell like? Now, if you're a mushroom collector or somebody who wants to eat mushrooms, presumably you have to have a good understanding of what these words mean and how to recognize it with your nose, and to make sure that what you smell as creosote isn't something that somebody else would smell as anise or some of these other smells. If it turned out that the smell was anise or almond, yes, then apparently the mushroom is edible. Does that mean that every single mushroom whose odor was anise or almond was edible? Again, here you probably would assume that that's the case, right? You don't want to be caught with this setting where we say, 90% of the mushrooms that smell like anise are edible, and then make a decision based on that your mushroom is edible. Because the 90%, if you're in the 10% of cases where the decision is the wrong one, that's a catastrophic outcome. You're making an error of type 2 here, or error type 1, depending on how you've decided to set things up, and that is not a pleasant error to make, right? Now, as it happens, our specific mushroom, its odor was none. Again, would you be able to recognize that there are no odor? There is no odor. What if you were congested that day? Is there an odor or isn't there? At any rate, let's pretend for a second that we agree that there's no odor. What this model is telling us is that when there is no odor, you don't have enough information to make a clear-cut decision. You have to ask further questions. What that might mean is that in your data set, whenever you have observations, objects that have no odor, we don't know if there's too many cases where it's poisonous, too many cases where it's edible. Let's see if we can somehow extract the information by asking questions of the other variables. So the other question would be to ask, what's the spore color? If the color is black, brown, buff, no idea what that is. Chocolate, green, chocolate, orange, and yellow, then it's edible. Go for it. Knock yourself out. If it's green, don't touch it. We're not saying that green spores are always going to be poisonous, but mushrooms with green spores that have no odor, mushrooms without odor that have green spores, these are poisonous, according to the model here. But mushrooms that have no odor, together with white spores, which is the situation for Amanita muscaria, we don't have enough information. We need to ask a further question. Habitat, and then eventually you can get to gill size. There is in the original data set, there is a cap color variable. I didn't include it here because I didn't want to go too far into the model, but you could have, worked with that as well. As it happens, if you follow the decisions for the specimen that we have, Amanita muscaria, we would conclude, based on all of these questions, that the mushroom is poisonous. Great. And it's simple. We don't need to eat it. Forget about the model you've just seen. Here is a picture of a mushroom. Would you eat this mushroom or not? Show of hands, who would feel comfortable eating this mushroom? Show of hands who would say, forget it, Pat, I'm not touching this mushroom. Right? What is making you say, I'm not touching this mushroom? So lack of experience with this specific mushroom is sufficient to say, I'm not touching it. I see here color. Yeah, it's a red mushroom, right? And red mushrooms, I'm like, no, just flat out no. But based on the data that I had given you here, that's not part of the picture. We're using data or information which is external to the data set to make a decision. And in practice, when you work with data, that's also an option which is available to you. Your models cannot go outside of the data. They don't have the ability to do that. You have the ability to provide context with your external knowledge. Humans have this ability. There's something dangerous about letting the model decide for yourself entirely what you will be doing. The models propose options, suggestions based on the data, but if you surrender your agency and you let the model decide what's happening all the time, you're not actually doing data analysis the proper way. Okay? You have to agree to retain some agency. Ultimately, the decisions have to come from human beings. Your data analysis decisions. You can't just run a model automatically and accept whatever it outputs as the sacred truth. Would you have trusted an edible prediction? Let's say we go through this model and the output says, no, it's edible. Would you have trusted this even though you had never seen the mushroom? Okay. So for the mushrooms, you don't, because the price to pay if the model is wrong is too high. Why do we accept model predictions in general? At some point, you might have worked up enough experience to realize that the model always agrees with your intuition about mushrooms, in which case, even though you've never seen Amanita muscaria before, since historically the model has done a bang-up job of making predictions, you might decide to take the plunge, a leap of faith. But you need to really know the context and you need to really know the model in order to be able to take that plunge. Where is that model coming from? For all you know, I just made up a model. I built a tree, I posted it there, and I said, trust me, this is a real model. And it looks like a real model. I mean, perhaps you've never seen one that's drawn quite like this, but it literally allows you to make decisions. It's a real model. But you don't know where it came from. What is it that you would need to know in order to trust the model, and so consequently also to trust the predictions? Do you just trust the model because it looks like a model? You have to have some understanding of what's going on under the hood, how the model is built, what the risks and the likelihoods of the model being wrong are. what is the cost of making mistaken classification here? It's a huge cost.